Good. So this is tutorial number 1. So we've been through 7 lectures, including the introductory class. So today we'll be solving the problems from tutorial sheet 1. Now remember that this course is all about learning how to solve heat transfer problems, design equipment, and so on. So you should be comfortable with the ideas, but you also should be comfortable with implementing them. Okay, there's no point having an idea for an engineer like us without any knowledge or any experience of how to use them for either solving a given problem that's given to us or designing an equipment that involves some sort of heat transfer. Okay. So today we'll be solving these problems on the board, but I won't be solving. I won't be putting numbers and giving you the final answer. These are things you can work by yourself, but I will definitely give you the idea as to how to proceed so that you can move in the direction of solving the problem. Okay, so let's start with problem number 1. So these problems are taken from the textbook in Coursera. So problem number 1 is in the tutorial sheet is 1.56 from the book. So do you want some time to go through the problem? Is there anyone who has not gone through the problem? If you do not say anything, then I'll start working on the problem straight away. It seems that most of you have already been through the problems. So that's okay, so that's good. So the first one, it's about thermal processing of semiconductor materials. So while we go through the problem, we just won't dive into solving it. We'll try to understand the physical phenomena as well, because it's very important to understand how heat transfer is applied. And these problems have been taken in such a way so that they give you an idea of the application of heat transfer. So let's try to understand and appreciate the problem as well. So this one's about thermal processing of semiconductor materials. So you have a process called annealing that you already know about. So this is carried out for silicon wafer to give it some sort of structural strength, the crystal structure. You want to develop the crystals and so on. So that process is carried out using the arrangement that's shown in the tutorial sheet. So what you have is you have a thin wafer, which is 0.78 millimeters thick. So this is our silicon wafer, which has a thickness denoted by L. Okay, so this is less than a millimeter thick. That's how thick silicon wafers are. And the process for annealing this includes an evacuated chamber. So you have this in a chamber. Okay, so it's evacuated. That means you're trying to remove as much air as you can, so that there is no conduction or convection because of that. So the only mode of heat transfer you have here is radiation. So what you have is you have this evacuated chamber, which is at a temperature of, we call it T surrounding, which is 27 degrees centigrade. So this chamber is radiating some heat as well. And then you have heating lamps, which are the ones which are used for heating this silicon wafer. Okay, so these lamps, they provide a total flux of 3 into 10 raised to the power 5 watts per meter square. Okay, so lots of flux. This is the flux that's given to us, not the temperature. So that's the amount of watts per meter square that's being emitted from the heating lamps, the very hot lamps. And then you are required, it's a gray material, so it's given to us that we can assume that the epsilon and the emissivity and the absorptivity are equal to 0.65 for this wafer material. Okay, the silicon wafer. And thermal conductivity of the wafer is given to us as 30 watts per meter Kelvin. It's not a very conductive material. Remember, silver was approximately 400. So this is not a very conductive material, but not quite insulating as well. It's not 0.01 or 0.02 as you typically have for insulating fillings or materials. And we have measured the temperature on the lower surface of this wafer, and that was found to be 997 degrees centigrade. So this is the wafer lower, which is 997 degrees centigrade. Okay, so this is what's given to us. So we have figured out what all is given. Now, what's being asked here is that we want to avoid the warping of the wafer. Okay, so if there's a lot of delta T between the lower and the upper surfaces of this wafer, then you know that there will be different expansions, and then that may cause the bending of the wafer. Okay, so or warping of the wafer. So you don't really want that. So for that, you can ensure that the temperature difference between the upper and the lower surfaces should be less than 2 degrees centigrade. Okay, so excuse me. All right. So let's say that in this situation, the temperature of the wafer on the upper surface is TWU. Okay, so this is what we have to find, and then we'll check if this upper temperature minus lower temperature is more than or less than 2 degrees centigrade. So what's ideal is that you would want to have this temperature, upper temperature, the difference between this upper and this lower is less than 2 degrees. So that is what exactly that is required. So is the problem clear to everyone? All right. Well, so what we do is we do an energy balance here. So the aim is to find TWU. Okay? So for that, what we do is we do an energy balance. In fact, the easiest one to do is to do an energy balance through a control surface. Remember the first lecture, we talked about the idea of using control surfaces. So we can assume a control surface, a very thin one, that is passing through the top surface of the wafer. In this case, in the surface is extremely thin. It's a surface. It's not a volume at all. So what happens is whatever enters the heat, the watts that enter is equal to the watts that leave the surface. So when I do an energy balance, let's do it. Let's probably do it here. Okay. So this is our control surface. Okay, so this is the same as this one. And you have this QS is the watts that is entering. So I'm not put a double prime. Double prime is the watts per meter square. So let's, since we're talking about the complete surface, so we'll say the total watts that are entering. This is QS, and then some amount of heat leaving from the top because of radiation, the emission that's happening from the top surface of the wafer. So we will call that Q radiation, RAD. Okay. So this radiation is the net radiative exchange from the top surface of the wafer, and then this control surface that we have, there is some energy leaving because of conduction, because the heat is getting conducted into the wafer. That we call Q conduction. That's it. That's the energy balance we have in this problem. Nothing else. So if we do that, if we write these in terms of the temperatures, then that should give us the expression for finding the upper wafer temperature. So let's do that. So this QS. So I can also write this balance as QS equals Q radiation plus Q conduction. And QS is given as 3 into 10 raised to power 5 watts per meter square. But you also have an absorptivity of the material. So that is 0.65. So what that means is, whatever irradiation falls on the surface, only 65% of that gets absorbed. So this becomes 0.65 times 3 into 10 raised to power 5 times, and then this is watts per meter square. So you need the top surface area. Let's see if that's given to us. Well, this surface area is not given, but that's okay. So everything can be written in terms of A. So I'll simply write this times A. Okay, so A is the surface area of the wafer, top surface. Okay, so this becomes my QS. And then Q radiation. Q radiation is the energy that's emitted, the net one, minus the energy that's absorbed from the surroundings. So again, remember the first lecture. So this was Q radiation was the emissivity, epsilon, times the Stefan-Boltzmann constant, times T upper to the power 4 minus T surrounding to the power 4. I guess you can see whatever I'm writing in this. If not, then please let me know. And then you have Q conduction. So Q conduction, again, this is a simple 1D situation. We can assume a one-dimensional situation, a steady state one-dimensional situation. So we know that Q conduction here is nothing but your K times the temperature difference. It's a linear profile. So all you get is dt by dx becomes delta T by L. So this becomes T upper minus T lower divided by L. So again, this is a tutorial. So if there's anything that is not clear, please feel free to stop me and ask. Okay, so that's it. So epsilon, we also need to have areas. I forgot to write that. So you need to have an A on here, and you also have an A here. So A gets cancelled. We don't need the value of A. So you can see that epsilon is known, that's 0.65. Sigma is a constant, the Stefan-Boltzmann constant. T surroundings given to us, that's 27 degrees centigrade. So make sure you convert that to kelvins because the Stefan-Boltzmann law includes this with T in kelvins. Don't make the mistake. And then again, T wall upper is what we have to find. So that's the unknown here. And then T wall lower is given to us. That is 997 degrees centigrade. Then L is the length, the thickness of the wafer, that's given to us. And K is the thermal conductivity of the wafer, that is also available with us. So when you solve this, you can find the upper temperature of the wall. Now, make sure you practice this because you have T to the power 4 here and so on. So you must get used to solving this quickly. That will help you in your estimates as well as in solving problems in the exam. So when you solve this, you will get your T wall upper. approximately as 1000 degree centigrade. So what that means is your delta T is more than 2 degrees centigrade. That's 3 degrees centigrade here, which is not good because this will cause the warping of your wafer, and that will damage your silicon wafer. Okay. So that's all for the given problem. Any questions?
Sir, hello. Hello.
Yes, please.
Yeah. Sir, why we didn't consider anything about the control surface at the lower end of the wafer?
Abhishek, I can't hear you properly. Let me try to increase the volume on my speakers. Can you also try to speak a bit loudly or go close to your microphone?
Yes, sir. Sir, why we had considered the control surface at the lower end of the wafer,
Here?
lower side? Yes, sir. Don't we have the sufficient data for that? Like all the heat coming from the radiation, conduction should go into the radiation at the lower end also. We haven't talked anything about that.
Hmm. So good point. So you're saying that what's going through the lower end, well, there's nothing that's given to us as to what's happening below the lower end, right?
Okay, sir. So we don't have the sufficient information.
Right. All that's given to us is what's happening on the top end. So all we did was we measured the lower end temperature using a radiation thermometer, but we did not. We have no idea as to what's the heat flux exchange at the lower end. Of course, energy has to leave because it's a steady state situation, but we have no information on that. But if we had the information, we could have used that. But yes, you're right. You can choose any surface you want. Ultimately, that's the idea is to have an energy balance in this case. So the conductive Q conduction will always have your P wall upper. Sorry, this one. You can always use that to find. So you're right. So you could have used the lower surface as well. Any other questions? Okay, so while I raise the board, please go through the second problem in the tutorial sheet. So let's start with the second problem. The second problem is also taken from the book. This is 2.5 from the book. Okay, so this one's saying that you assume steady state one-dimensional heat conduction through the symmetric shape that is shown to us. We have this kind of a symmetric shape. It's like a fin that you have, and it's given that the qx, that's the heat, the watts that are entering are given to us here. So you can assume steady state and one-dimensional heat conduction. So they're saying that assume that there's no heat generation. You can also assume that Q dot is 0. And you have to derive an expression for the thermal conductivity K as a function of X. So this is a non-homogeneous thermal conductivity situation. The K is changing, and it's given to us that the area changes as a function of X. And this expression is given as 1 minus X, but X equal to 0. So this is X equal to 0. So at X equal to 0, you have area as 1 units, and as you go along, it linearly decreases, as you can see from the figure. And the temperature distribution as a function of X is also given to us. Okay, so it's cubic. We have 300 times 1 minus 2x minus x cubed. Okay. And this qx value is given as 6,000 watts. It's a very straightforward problem. You have some heat entering, and that's getting conducted into this fin, and the area changes as 1 minus x, linearly goes down, and the temperature changes cubically. So what we have to do is we have to find the function T as a function of x. So the only idea we need to understand here is that whatever heat's entering from the left hand side is equal to the heat at any given cross section. If I take any cross section and do an energy balance, I will see that it's a steady state situation. So whatever enters has to leave. Otherwise, it may start collecting and increasing the temperature inside that control volume. But that is not the case. So that means that Q at any given cross section, well, this Q, so this is at any given cross section, so which is as a function of x, is minus k, minus k a dt by dx, and that is equal to 6,000 watts. You take any cross section, you will see that the heat that's flowing from left to right in that along that cross section is 6,000 watts. So we can use this now. This becomes minus k, and the expression for area is 1 minus x, and dt by dx becomes 300 That's it. You can find the value of the expression for k from this. So there's nothing much here. So you will see that k becomes 300 divided by 1 minus x times 2 plus 3x squared. Sorry, 6,000 divided by 300. So let's just write that. So this becomes 20. Okay, so you can see that there's a similarity here at x equal to 1. So at x equal to 0, you get this becomes 20 divided by 10. That is 20 divided by 2. That is 10. So at x equal to 0 on the left hand side, the K value is 10 watts per meter Kelvin. And as we go along, the K value approaches infinity. So it increases and it approaches infinity as x tends to 1. So that's pretty much what this problem is about. Any question on this? So let us go to the third problem now. So this is 3.15 from your book. So this is about designing insulating walls. It's an extremely important practical idea that is used for especially in cold places like the one we have here in Mandi. Actually, the walls that we have are similar to what is given in the problem. So you have a composite wall that includes an 8 mm thick hardwood siding. So this is hardwood siding that is 8 mm, 8 mm. So that's a hardwood. That's for the exterior side of the house. Okay, then you have 40 mm by 130 mm hardwood studs to connect this to a wall board. So this is the outside, and then you have the inside of the wall, which is a wall board. This different material. Okay, so this is then you have studs to connect this. You need to give it some structural strength, otherwise they'll collapse on each other. We are looking at the cross section. Okay, so this is so we're looking from the top of the building. This is the cross section of your composite wall, and then you have some insulating material that's filled here, so that you minimize the heat loss. And this insulation is made up of glass fiber. Okay. So what's asked to us is what is the thermal resistance associated with a wall that is 2.5 meters high and 6.5 meters wide. So basically, one such system is 2.5 meters high, okay? And then it is 0.65 meters wide. So what you have done is you have connected 10 of these, and then you would want to know what's the total thermal resistance of the assembly. Again, a very straightforward problem if you understand what's happening here. So let's take one of these and then calculate the thermal resistance of that, and then we'll put them in parallel. So what we have here is, we can draw here. Let me create some space in the left. So first you have the resistance because of the hardwood siding. Then you have two resistances in parallel. One's because of the insulating material, and the others because of the studs. So I'll call it R stud, and this is R insulation, and this is R hardwood. And then you have another resistance which is the R wall board. So think of it in this sense. So whatever heat's traveling through here, part of it goes to the stud as conduction, and the other part goes to the glass fiber as conduction. And then both of them together go to the wall board as conduction. You have to make sure, you have to assume here is that they are all isothermal walls, so that there is no heat transfer happening this way. I mean, that's an assumption, but we have to start with something. So this is the net thermal resistance circuit that we have here. You can put the values of the thermal conductivities. I'm seeing the tables and the charts that are available in the book, and then you can get the net thermal resistance of this one assembly that you have here. But remember, you have 10 of these, so the total heat transfer is happening it is split into 10 of those. So that means the net resistance that you get here, you have 10 of these in parallel. Okay. Well, that is all. There's nothing more here. Any questions? So typically in a tutorial, I would go to the class and let you solve problems by yourself. But here, since we're doing things online, it's a waste of resource if I just sit and do nothing in this video. So usually I would expect you to try the problems by yourself beforehand, and then the tutorial becomes much more effective, because when you try to solve something, you get stuck somewhere. That is where you realize what questions you have to ask. Otherwise, I'll just skim through the ideas and leave it to you to solve them and get the answers. So we have around 10 minutes and 3 problems. So let me see which one is the best one to discuss. So this problem number 4 is about a firefighter's protective clothing. So let's do this problem. There's an interesting idea that I want to discuss through this problem. So please go through problem number 4 and then we'll start discussing it. So it talks about a firefighter's protective clothing, which is referred to as a turnout coat. So it's typically constructed as an ensemble of 3 layers separated by air gaps. So let's draw these layers. So the first one, so this is your fire side. So the first one on the outside is called the shell. Okay, then you have a 1 millimeter air gap. Then you have another layer which is called a moisture barrier. Then there is another 1 millimeter of air gap. And then you have a thermal liner. So that's the inside and that's the outside. Okay, so in the air gap, the heat transfer happens because of conduction as well as radiation. Because the radiation is always happening. So there's both modes of heat transfer. So problem part A says represent the turnout code by a thermal circuit. So again, quite straightforward. So you have a shell resistance, and this is purely due to conduction. So this is R shell, and then a part of it goes as radiation, and then a part of it goes as conduction in the air gap. Okay, then again you have an R moisture barrier, which again then splits into two resistances in parallel, one the radiation and one's the conduction. Okay, let's call it 1 and 2 because they may be different. And then you have your R thermal line. All right, so that's your net circuit that you have here. But when you start solving it, you would see that R radiation, it depends on T to the power of 4. If I write this R radiation, then so if you read the problem, it says that you can assume the a linearized radiation coefficient for the gap. So they say that like you have in Newton's law of cooling, you can also have an R radiation, H radiation, that is given as sigma T1 plus T2. T1 and T2 are the two temperatures, so let's call this T1 and this is T2. There's radiative exchange between the two, and then you have T1 square plus T2 square. So we have again discussed this of using a heat transfer coefficient for radiation. But in this case, what you see is when you write this radiation coefficient, that depends on T1 squared, T2 squared, and so on. So what you can do is, if these temperatures are high, you can assume that T1 plus T2 is approximately equal to twice some T average. So if you assume that, then this becomes sigma. You have 2 T average, and then you have twice T average square. So this becomes 4 sigma T average cube. You know, T average is a function of T1 and T2, but you can assume that, and then this T average is given to us as 470 kelvins. Again, in a real situation that won't be given to us, but for the problem solving, that's given to us. So if you put this number, then we can get the value of R radiation as 1 divided by HA. H becomes a known value in that case. Okay, so that's an idea I want to discuss. It's a very common idea that we do in radiation problems while calculating resistances, that we tend to, because these numbers are quite high, so the difference between them is not that large. So we can assume that T1 plus T2 is approximately twice T average. Okay. The rest of the problems straightforward, and you can find the net resistance, and then you can find the temperature of the inside. So what typically we do as designers is that when we design a suit, you design it for a situation where you would rate it. So this suit is rated for a maximum for an outside temperature, maximum outside fireside temperature of, let's say, 500 degrees centigrade. So what that means is that you would want to calculate the inside temperature given the worst case scenario of 500 degree centigrade outside. Okay, so once you have the resistance, net resistance, you can calculate the inside temperature and then see if that inside temperature is too high. So if the inside temperature comes out to be 100 degrees centigrade, then that means that is not a good design, because you don't want 100 degrees centigrade touching your skin. So if I say that comfortably the firefighter can bear a heat of, let's say, 50 degrees centigrade, which is not that bearable but still manageable for a short duration. In that case, for the worst case scenario, if I know 50 degrees centigrade here, for a given design, I can calculate what's the maximum fireside temperature the suit can handle. So this is typically what you would do in such a problem. Any questions? All right. So the next problem, I won't solve it. It's again the ideas we already have used. So let's go through it. Well, I'll draw the diagram. In the fifth problem, we have a power transistor. We have a power transistor. And this is encapsulated in an aluminium case that is attached to its base to a square aluminium plate of thermal conductivity, that's K. So basically, you have an aluminium assembly. So this is what I've drawn as an outside assembly, and you connect this assembly through bolts onto an aluminium base plate. Just to give it more area to lose heat, because it's a power transistor, it's supposed to generate heat. Okay, so you have a base plate here. It's aluminium, and this is aluminium casing on the power transistor. And this again is it's enclosed in a completely insulating enclosure. So the idea that's important here is these bolts. So what you do is you tighten the bolts onto the base plate, because you have two surfaces contacting each other, and this power transistor casing is going to lose heat through conduction to the base plate. So to increase the or to decrease the contact resistance, you would want to tighten the bolts so that the pressure between the two is high. So the contact pressure is given as 1 bar. That is 10 to the 5 newtons per meter square. And if you see the tables for a given roughness of the materials, the composition, as well as the contact pressure, the thermal resistances are tabulated from experiments. So you'll have to go to tables, or it may be given to you in exams. But in reality, you would want to decide how tight these bolts should be that decides the pressure, so that you have the optimum thermal resistance that you can, the contact resistance that you can have, because you would want to minimize that contact resistance to maximize the heat loss. Okay, everything else is are ideas which you already know, but the only new idea here is to calculate the contact resistance using the contact pressure. So don't forget to include the contact resistance in the circuit. So when I draw the circuit, then let's say that this is T, they call it TS, C. So this is your TS, C, which is the same as the complete block. And then you have an RT contact, thermal resistance because of contact. And then you have your R because of conduction in the base plate. So remember to include this contact resistance, which otherwise you may end up over predicting your rate of heat transfer. Okay, so we will stop here. I'll leave it to you to work on the 6th problem by yourself. It's a quite straightforward problem. So I hope this tutorial session was useful. So in tomorrow's lecture, we will go back to our conduction, and we'll be working with situations where you have heat that is generated inside volumes. And we'll talk about volumes which are not rectangular shape. So we will work with pipes or wires where you use radial coordinates too. So we will write the heat conduction equation in radial coordinate system. Okay, so I'll stop the recording now. In case you have any further questions, please feel free to ask.